Hi everyone, welcome to this new lecture Fluid Mechanics. In this lecture, we'll derive an expression for boundary layer thickness, shear stress and coefficient of drag from the velocity profile of laminar boundary layer. So this kind of expression or this kind of questions can be asked in different ways, either in maybe derivation ways or it may be given in the problematic. So the problem here I have taken for the velocity profile of laminar boundary layer flows with a given rate of equations given. The velocity profile is given this one. Small u by capital U equal to 2 into y by delta minus y by delta square. Find an expression for boundary layer thickness. So first one we need to find out boundary layer thickness. Then we need to find out the shear stress and next the coefficient of drag in terms of Reynolds number. So these three things we need to find out in terms of Reynolds number. So here the question already given in the velocity profile is given, and to solve this one we need to go to our previous video lecture, like what we have discussed during the von Karman momentum integral equation. So there we have got one expression. I'll tell that one, but before that let me write this velocity distribution. So the velocity distribution is written by small u by capital U. This equal to 2 into y by delta and this minus y by delta square. Y by delta square. This is the velocity distribution given. And actually we need to go to the, as I told you, that von Karman momentum integral equation. So that we have seen in our previous lecture. So let me write this equation. From that von Karman equation, what we got, von Karman momentum integral equation, there actually we got an equation like tau naught in terms of shear stress. I'm writing tau naught rho u square equal to del by del x whole bracket integration 0 to delta, and this is small u by capital U bracket start again 1 minus small u by capital U into dy. So there this value was theta, that's why we had written here tau naught by rho u square equal to del theta by del x. Final equation what we got for the von Karman equation. But before to that, actually this is the this was the equation what we got. Now in this what is the value is given, velocity distribution is given, u by small u by capital U is given already. That is the velocity distribution. So what we need to do, we need to put this value of small u by capital U in this equation. Now here, how many small u by capital U is there? Now here one is there, another one is here. So that means at the two places we need to put the value of this. So this will be a lengthy derivation type. So first let apply this value. So after applying we'll get del by del x bracket start 0 to delta, and here the total equation we need to write here. Okay, so that will write in again square bracket will give it here. So this will be can be written 2y by delta, and this is y square by delta square. Just I have multiplied this 2 into inside, and this is whole square I have done. Okay, and this again bracket will be started because you can see here bracket is there. So this is 1 minus, again that we need to write here. So this one we can write on a bracket here like 2y by delta and minus y square by delta square bracket close. This is of dy. Okay, then again this one we can write del by del x, again square bracket start integration 0 to delta. This one we can write again 2y by delta minus y square delta square. This one we can keep in a bracket, actually normal bracket we can also keep it, no issue. And this is square bracket start, and here what will write 1 minus 2y by delta, and this one what I'll do, just I'll put this dy inside this. Okay, so y square by delta square bracket this one you just write here bracket close, again dy and whole bracket this one. Initially it was in the outside, now I kept it inside this one. Now what we'll do, we'll just multiply this term each other. Okay, so once you multiply one by one term, what we'll get, it will lengthy equation like 2y by delta. First will multiply here, again y square by delta square, it will be multiplied again. So directly I'm writing 0 to delta 2y by delta into 1. So this is 2y by delta only. Again minus 2y by delta, this one 2y by delta into minus 2y by delta, that is minus will be there, and this is 4y square by delta square, 4y square by delta square, and this is again 1 2 completed. Next 2y 2y into y square, that means 2y cube. So 2y cube divided by delta cube. Okay, this is one part completed. Now next minus y square by delta square is there. So that is minus y square by delta square, and plus minus into minus plus. So y to the power 4. This is y square is there, and here also y square is there. So that means y to the power 4. No, I actually before that one more term is there. This one 2y. So that means okay. Let's write. Already I have written this one. Let's write y to the power 4. Again one more term will be, this is 2y cube by delta cube. This is bracket close and whole to the power dy you can write. Okay, this is what I have done, multiplied. Now next step what I'll do, again del by del x. Here what I'll do, integration the total whole term 0 to delta, and just to solve this, like what are the things will be cancelled here that we can cancel, or we can add it, means we can add it. So this is square bracket here 2y by delta, and this is 4y square, this is 4y square, again y square by delta square. So this is 4 and this is 1 minus, so 5. So 5y square by delta square, and similarly again you can get 2y cube delta cube. So here 2y cube delta cube plus plus, that means 4y cube by delta cube. Just we need to check the symbols, okay, the signs whether it is correct, same or not. Then again this is y to the power 4 by delta to the power 4. Okay, y to the power 4. This is actually minus, yeah, minus. See, actually here it is yeah, this is minus y square, yeah. And here actually it is this one, actually we need to take it, this will be, I think plus will be there, or 1 minus this one, so 1 minus of this value. Okay, so finally what we can write here, this is y to the power 4 by delta to the power 4. Okay, correct. Now y to the power 4 delta to the power 4, how many terms are there? This is 1 only, and any other term is there? No. So here what will get here, y to the power 4 to the power delta to the power, that will be minus is given, yeah, minus is given, yeah, correct. So this whole to the power dy. Okay, now again one more line I'll write for this, like delta by del x. This is square bracket start. Again I'll just integrate this. Let integrate this one with respect to 0 to delta. So this will be 2, this will be dy with respect to dy. So 2y by delta dy integration, that means 2y square by 2 delta. Okay, and this is minus again 5 into y square integration dy, that means y cube divided by 3 delta square. I am doing this integration of this whole. Now this will be like plus 4 into y to the power 4 by this will be 4 delta cube minus this is 4y to the power this will be actually 4y to the power 5, or we can say no, y to the power 4 is there, that means y to the power 5, y to the power 5 by 5 into delta to the power 4. Okay, so this is whole, and 0 to delta. Now what we'll do, we'll just put the value of this 0 delta, upper limit and lower limit here. Then what we'll get here, 0 del by del x. This one you can see it will be cancelled, and here also it is cancelled. Okay, so what we'll get here, put the value delta here. So delta in place of y square, that means delta square by this 2 cancel. So delta square by delta. Okay. Similarly, minus 5 by 3, and this is delta q by delta square. Okay. Now this is plus delta to the power 4 by delta to the power 3, and this is minus delta to the power 5 by 5 into delta to the power 4. This upper limit, lower limit we have done. Lower limit is 0, so no need to use this one. Now finally, if you see what will get in here, so let me write this equation. So after cancelling this value, what will get? Del by del x, and this is bracket start, this is delta minus 5 by 3 delta, because see, this is cancelled and this 2 to cancel, 1 will be there. So similarly again plus delta will be there, and minus delta 5 delta 4, so delta by 5 will be there, delta by 5, bracket close. Now if you solve this one again, here just I'll write this one like del by del x, and just to solve this one, so in the denominator we'll get 15. Okay, and top in the numerator we need to write like 15 delta, and this is minus 25. Yeah, this is, I hope, yeah, 15 delta and 25 delta actually. One is minus 25 delta, so 5 by 3, 5 by 3, 3 is a 15, that means 3 into 5 is 15, so 5 into 5 25, so 25 delta, then plus this is 15 delta, 15 delta minus 5 delta, sorry, minus 3 delta, bracket close. Now if you see all these things cancelled, then what we'll get finally, we'll get here del by del x, del by del x, here 15 30, and minus term is there, how much? So 30 delta minus here 25 3, so that is 28 delta, and divided by 15. Now if you solve this one again, what will get? Del by del x, del by del x, bracket start, 2 delta by 15, 2 delta by 15. So 2 by 15 we as a constant term, let's take it to outside. So 2 by 15 del into delta with respect to delta x. So this one given equation 1. Now this value actually what we got here, this is we got the delta tau naught by rho u square. So what I'll do here, I'll just write tau naught equal to, I'll just take this term to the other side, that means rho u square, I'll take it to the left hand side as a right hand side, and here this term 2 by 15, and del you can write this is delta, and here you can write this is, this one also you can give it in a square bracket also, no issue. And finally what we can write, this is 2 by 15 rho u square, del, this is delta divided by del x. This one we can give equation, or else here no need to give equation 1, directly we will give the equation 1, because after solving only we are getting this one. Okay, now this is only tau naught we have solved here. Okay, now we know that the shear stress at the boundary in the laminar flow, if you see in the laminar flow, when the flow is in the laminar condition and the shear stress at the boundary, okay, that value will be given as per the Newton's law of viscosity, what we have seen. That means the tau naught equal to mu into du by dy, that equation is there. So as per this we can write, as per that Newton's law of viscosity, we can write tau naught equal to mu into du by dy. Okay, and this is actually near to the boundary, that means at y equal to 0 at this point. Now if it slowly to be moved, then we will get a velocity boundary layer like this. Okay, now this one we can give equation, this is let equation 2, and the main equation what is given, let give it equation 1, and this one we can give equation 3. Okay, now from the equation this we can get like what we can write, u equal to, here the first equation what was there from the equation 1, that's why I've given equation 1 here now. So from this equation 1 what we can get, like small u equal to capital U, and this bracket start, and this one we can write, already we written 2y by delta, and this is y square, this is y square by delta square, and this is bracket close. Now just to derivative of this, then what we'll get, just make a derivative of this, and that is du by dy. This is velocity. Now put just derivative with respect to dy, so what we'll get, dy equal to u, and here 2y by delta, so we'll get only 2y delta, dy by dy, that is 1, and this is here also we'll get derivative of this y square, that means 2y by delta square. Okay, and here u is the constant term. Now we can write, so what we'll get, one more term we can write, like du by dy at y equal to 0, at y equal to 0, what we'll get here, this part will be cancelled here. So finally what we'll get, 2 into, at y equal to 0 we can get 2 into y by delta. Okay, now substitute this value in this equation. So substitute the value in this equation, then finally what we'll get, let me write here, tau naught equal to mu into 2 capital U by delta. So this is nothing but, we can write 2 mu capital U by delta. This is equation 4. Okay, this is equation 4. Now what we got equation 4, this is also tau naught. Now previously if you see the equation 2, what we got, that is also tau naught, that means shear stress we got two values. Now we need to just equate these two equations, equation 2 and equation 4. Now similarly what I'll write here, just equate these two equation 2 and 4. Then what I'll get, just let me write here, this is, we got this equation 2 by 15 rho u square, and this is delta bracket delta with respect to del x equal to, this is 2 mu capital U by delta. This is the equation here. Okay, it is here, it is delta. Now what we'll get here, one more term I can write here, like del by, this is delta with respect to del x, and this is, let's take this term to other side, because both side 2 is there, it will be cancelled. Okay, and 1 u also we can cancel it here, like here u square, and u is there, so only 1 u will be here. So what I'll write here, this is delta by del x. Here 15 term I'll take it to the other side, 15 mu capital U divided by, okay, rho, only rho will be there, sorry, rho u square here actually. So here it is, u will be not there, only u, because already u we have cancelled here, this u we have cancelled here. So what will get, only rho u. So again one more term what we'll write, we'll take, like, write delta equal to this dx, let's take it to the other side, that means 15 mu by rho u, this is del x. Okay, now this is, now we know that this is one equation. Okay, so next time I'll write in the next page. Yeah, so we know that delta is the function of, we know that delta is equal to what, delta is the function, it is the boundary layer thickness. We know this is boundary layer thickness. So this is the function of, length, that means this is a function of x. X is nothing but the suppose length is there. So in the partial derivative, what can write, we can write, this is the partial derivative can be written in the total derivative. So the total derivative, what will write, delta, this is on behalf of del, like the derivative of this, it means full derivative, that is the partial derivative I have to convert it into total derivative. So that is nothing but 15 mu by rho u dx. Okay, and now we need to just integrate this equation. Now just integrate this equation, what we'll get, let me start from here. Okay, After integrating, what we'll get here? Integrate of this one. So we'll get delta square by 2. Delta square by 2. And this is equal to 15 by rho u. These are the constant terms are there. So there will be nothing changed. Integration of dx. So that will be x. Here x plus and constant term c. So now here if you see this mu by rho into u, this is a total constant term. Okay. This is a constant term is there. So nothing is there. That means all these things will be constant. Only dx is there. So that we have integrated. Now here what we need to consider is the value of x equal to 0. Length is 0. Delta is 0. Okay. So by putting the value of x equal to 0, that means at the starting of the plate, and delta equal to boundary layer thickness also obviously 0, there is no boundary layer thickness. So that means leading edge type. The leading edge type, this is the condition. Then if you put the value here, then what will get here? Then we'll get c equal to 0. Then just put this value in this equation. So what will get? Delta square by 2 equal to 15 mu x by rho u, because c is already 0. Now this one again, what we can write? This one again, let me write in this way. Delta equal to, or delta square is there. Let me write delta equal to root over of 2 into 15 mu x divided by rho u. So now 30 is there. So that means root over of 30 mu x by rho u. Now if you just root over of this one, we'll get near about 5 point something will get value exactly. So let me write here again. The delta part is nothing but boundary layer thickness. We'll get suppose 5.5. Let me take average of this. And here what we'll get, like mu into x by rho u. So mu x is there. Let me multiply one more x here, and here in the denominator also multiply one more x. So mu x square by rho ux. So now why I have multiplied x? Because I need to convert it in terms of Reynolds number, and we know that Reynolds number equal to what? Reynolds number equal to rho vl by x, rho vl by mu. So now rho vl by mu is there. Now this part rho vx by mu. Okay, so this is nothing but Reynolds number. So what will get right here? This is 5.5 and root over of, exactly if you root over of this, you will get some different value actually. So that also you can calculate here. Let me take it a calculator help. So yeah, here you can just 30 root over 5.48. So exactly if you want to write here, we can write this is 5.48 root over of, this is x square by Reynolds number with respect to x. Okay, because we know that R equal to rho VL by mu or rho Vx by mu. So this is our equation 5. Equation 5 we can give it this one. Okay, so this is the value of delta. Now this in this equation, if you see equation, okay, now this is one equation, this one, okay, anyway, in this delta, if you see mu, rho and u, these are the constant value, correct? So these are the constant value. Then thickness, we can say the thickness of the laminar boundary layer is directly proportional to the square root of this line equation of this one. Okay, equation of this. So what we can write here, so as we have converted this one into the in terms of Reynolds number. Okay, so what is our first let me tell you, we need to first calculate the boundary layer thickness. We have calculated in terms of Reynolds number. Now we need to calculate the shear stress. Okay, the first one is calculated, this one, this started from here. Now second one we need to calculate, see, I have calculated this delta in terms of Reynolds number, correct? So first equation solved. Second part is we need to solve the shear stress in terms of Reynolds number. So shear stress we can write what? Now from the previous equation what we can write, we know that tau naught equal to, here what we have got, 2 mu u by here delta. So now this put the value of delta in this equation, then what will get here? This is 2 mu u and divided by this whole term, what will write, like 5.48, and this is here, if I write this one delta value, then just I can write this, yeah, okay, here one more term is there, that is 5.48 root over of x square by 2x. So I can write this root over of part, I'll give it here. So only I can write x by root over of re x. Okay. Now again, what I'll write here, this one, if I solve it, then again I need to write, like, yeah, one more times calculator required, because 2 by 5.48 is there. So 2 divided by 5.48, 0.364 or 365 we can write. So this is 0.365 into mu into u by x root over of rex. Okay, so this is the Tauno term what we got here. Now actually we need to convert in terms of, as I told you, that shear stress, and that one more term is there, that is coefficient of drag. So this one we got, this one also we can say this is the equation. Now the third part is, the third equation is we need to convert into in terms of coefficient of drag. So the third equation, that coefficient of drag is nothing but CD. So to find out this one, we need to go to the like last lecture what we have written there. So there I have written the equation CD equal to, this is actually the ratio of drag force with respect to 1 by rho u square. Okay, and FD equal to, we know that from the Von-Karman equation, this is 0 to L, and this is tau naught B dx. This is actually where we got this one, we got from the Von-Karman equation. So again, what I'll do, I'll just write the value of, now tau naught value we got already. So let me put the value of tau naught here. So 0 to L, 0 to L. So tau naught value we can write here 0.365, and this is mu capital U divided by x and root over of re x, and this is b into dx. This is the equation. Now just we need to solve it. Just we need to integrate this, and we'll find the final value. So this will be 3.6, and this is mu u by x, and this is root over of rho. This is root over of, we can write this is rho ux by mu. This one I have written, this one, this value, rho u into x by mu. This is Reynolds number value, and this is b into dx. Now the same thing, okay, let me write here. So this one I can write, this is 0.365, and this is integration 0 to L, and here we can write this is mu u, and this is root over of rho u by mu, and into 1 by root over of x into b into dx. And again, in the next step, what I can write, just to write 365, and just if you integrate this one, integrate 0 to L, then what? Okay, integrate part which one with respect to dx. So which part of dx is there? Let take it to that one. Remaining terms, let take it to outside here. So this is constant part, everything. So this is into b, and now integration we can start here, 0 to L, and this is x to the power minus 1 by 2 dx. So here what we'll get, again you can write this is 0.365 mu into u, and this is root over of, you can write rho u by mu into, this is b, and here into, we can do after solving this one, x to the power minus 1 by 2, and this is no, here minus 1 by 2 was there, now we'll get 1 by 2, and this is 1 by 2. Okay, and this is lower limit, upper limit 0 to L. Now finally we can write this is 0.365 into, this is square root is there. Now if you solve this one, what will get, 2 mu u, and this is root over of rho u, this is by mu into b into root over of L. Just put the value of upper limit here. Now again, next what we can write here, just to multiply this 0.365, and this is 2 into mu. So this value, because I have taken this mu here, 2 mu u, yeah, this one. Now what we can write here, this is 0.72 or 73 something will get here, and this is b, okay, b mu u, b mu u, and what was there here, just root over of, what I'll do, rho u, this root over, just to multiply rho ul by mu, rho ul by mu. Now this one we can give equation 6. Now what we got here, coefficient of discharge, sorry, this is the coefficient of drag, the drag coefficient. So what we can write, 0.72 b mu u, and this is root over of rho ul by mu. Yeah, so what we can write here, this is 0. This one divided by 1 by 2 rho u square, 1 by 2 rho u square, because we know that this is the drag force. So up to now what we got, this is our drag force. Now here we can write coefficient is drag equal to this one, and here what we can write in the area here, actually rho au square, here it is rho au square, so a was not written. Now here we know that a equal to area of the plate. So area of the plate we can write, this is length into width, so we can write L into B. Now just put the value again. Now CD equal to, just write this 0.73 B mu u by 1 by 2 rho LB and u square. Now if you cancel this, what will get here? Again multiply is there, sorry, multiply rho ul by mu. And finally if you solve this one, we'll find out, like, yeah, again we need to do this, like, 0.73 into 2, that means 1.46. So 1.46, and root over of this will get like mu by root over of rho ul, and this one, like, if you hold root over of this, rho vl by mu, we can write this one. So finally we can write CD equal to 1.46, and 1.46 divided by root over of REL, This is our equation 7. Now this one, see, this part is actually rho VL by mu. If I consider, this is equal to RE, Reynolds number. Okay, anyway, so I hope you understand, like, though it is little bit lengthy, I hope you understand this equation, how to derive this. That means how the question can be given in any type, like, for a problematic, or it may be given in to derive the expressions. We need to derive the expression for the boundary layer thickness, shear stress, and the coefficient of drag from in terms of Reynolds number, where the velocity profile of the laminar boundary layer will be given. So I hope you understand this derivation. Still, if you are having any kind of doubt and query regarding this, you can give a comment on the comment box. Thank you all.